algorithms. So thank you.
Thank you, Juan. I'm of course very pleased to have escaped late winter in New York and come to this wonderful campus. So here are a couple of my collaborators who are relevant here, and I'm going to name a number of others as time goes by. So let's start with mostly the main decomposition methods are solvers for finite element models. So let's just remind ourselves about the very simplest finite element model. So we have a Poisson problem in a bounded domain, typically assumed to be Lipschitz, and with zero boundary conditions on the boundary. And then by integration by parts using Green's formula, we turn that into a variational problem. But we have the gradients here. And this should hold for all test functions, where the first derivatives are L2 functions, and the functions vanish on the boundary. So to get a finite element model, we introduce a subspace of this infinite dimensional space, a finite element subspace, which is defined on a triangulation of omega. That might be many triangles. And the space is spanned by nodal functions. So we have nodes which are the vertices of the triangles, and we have piecewise linear, in the simplest case, continuous piecewise linear functions. And the nodal basis functions are 1 at one node and 0 at all the other nodes, and so they are local. And when we plug this in and run with the test functions here, we get a linear algebraic system with a symmetric, positive, definite sparse matrix, which I call A. And in special cases, if you have a very regular triangulation, we end up with a 5 or 7 point finite difference approximation to the Laplacian. Now, to solve this system, we can use Gaussian elimination, and we can use Cholesky's algorithms, which exploits the symmetry and positive definiteness of this problem. But if you have 3D, then you have a quadratic growth that's best possible. It depends on the ordering of the equations, but you can never do better than n squared operations, and if n is large, in the billions, for example, then you have to turn to an iterative method rather than an exact method to solve the problem. So BDDC is a particular family of algorithms which turn out to be very effective. There are many different domain decomposition algorithms, but this turns out to be one of the very best. And so we are looking at to solve these finite element approximation problems with very many degrees of freedom. And we are exploring different classes of elliptic problems. In some sense, at one point I had a lot of students, and then you have to find different classes of elliptic problems for different students, right? And you go through a number of the classical models which already have been known in the 1800s. Okay, so among applications, we have elasticity problems, very important in mechanical engineering, and we have problems formulated in H-curl HDiv, and we also have things like finite element models for Reisner-Mindlin plates. All this we have done. Now, studies are mostly for lower order finite elements, for self-adjoint elliptic problems, but we also, in recent years, have worked very actively on difficult problems arises in isometric analysis, which is an alternative to classical finite elements. So all this aims to develop preconditions. So what is for the stiffness matrix, the A matrix? So what is a preconditioner? A preconditioner is simply an approximate inverse to the operator. And then once you have such a preconditioner, you combine it with a conjugate gradient or some other Krylov space method. And what matters now in terms of rate of convergence is the condition number of this preconditioned matrix. Now, we are primarily interested in huge problems with very many subdomains. And we would like convergence rates which are independent of the number of subdomains. And also we like the rate of convergence to decline slowly with the size of the subdomain problem. We can't make that constant, but we can have it slowly decline. So many of our bounds will also be independent of jumps of the coefficients between the subdomains. So the BDDC algorithms. What do we start doing? Well, we take our domain, omega, and then for the elliptic problem. And then we split it into non-overlapping subdomains. And the idea is to use solvers for these subdomain problems, but also, in order to get independence on the number of subdomains, we need another important feature, which is a global problem of relatively low dimension. So, now, if you look at the subdomain, nowadays, we run a subdomain problem on a separate computer processor, typically in a distributor or parallel computer. And they are often, nowadays, there are many, we have tens of thousands of degrees of freedom for each of these. And then we have a huge number of subdomains. So between the subdomains, which do not overlap, we have an interface. And the local interface for a subdomain omega I is simply the boundary of it, except for the boundary of the original assembled domain. So we assume that the subdomain doesn't cut through any elements. Each subdomain is a union of elements. So most of the finite element nodes now, which can be actually, for an H1 problem, elasticity, for example, we use nodes. For H-curl and H-div problems, the relevant geometric objects are actually element edges or element faces. But let's look at the nodes, okay? So most of the nodes will be inside the individual subdomains. And others will belong to several subdomain faces. Okay, we might also have degrees of freedom on the boundary, but that's not so relevant. Okay, so the degrees of freedom on this interface, they are partitioned into equivalence classes, which are the sets of indices. We look at the node on the interface and we ask, to which set of boundaries of subdomains does it belong? And that gives us an equivalence relationship. So for 3D nodal finite elements, we will have classes of face nodes, which are associated with just two local interfaces, okay? And classes of edge nodes and subdomain vertex nodes, which typically are associated with more. Okay, this is very important. So for H-curl, we have element edges, subdomain faces, and edges. And for H-div, we just have actually degrees of freedom on the element faces only. So that's, in some cases, simplest case. Okay, so these equivalence classes play a central role in the design and analysis and programming of domain decomposition methods. For example, communicating between different subdomains, you need to know, of course, for a certain node, to which other subdomains should you communicate. Okay, so the balancing subdomain, the BDDC methods were introduced by Dorman, who was a very talented man at Sandia, Albuquerque. in 2003, following the introduction of an equally important method called FETDP, which was introduced by Farhat and others in 2000. And these two families are related algorithmically and also have a common theoretical foundation. So the preconditions I used are based on partially assembled stiffness matrices assembled from subdomain stiffness matrices, which I call A of I. This is a stiffness matrix associated with omega. And we will look at a nodal finite element problem in 2D on the next slide. So the nodes will be divided into interior nodes, interface nodes. And the interface nodes will actually be split into a smaller set, a primal set, and a dual set, which are the rest. And here's the picture. So we have essentially a membrane model here, and what we have done is to insist on continuity, but just at the vertices of these subdomains. But we allow, so we have interior nodes here, which are not marked, and then we have nodes here, and for the finite element model, we should have the same value, but we allow multiple values for these interface nodes on these edges. Okay, so what's the benefit of this? Well, it turns out that the linear system for this different finite element model is much faster to solve. Okay, so here we have a subdomain matrix, and we have three indices. The interior, we have the dual ones, which are the edge nodes, and the primal one, which are the vertex nodes in the picture I just showed. And then, so this represents the energy contributed by omega I. And the whole model is just obtained by adding the energies up. That's called subassembly. So we enforce the continuity of the primal variables as in the given finite element model, and we allow multiple values for the dual variables when working with the partially subassembled model, which is here, right? Okay, so this has all actually the flavor of an important ordering method called nested dissection. So okay, so now if we put these things together, then we see we have a very nice structure. We have block matrices here which are independent of each other. They can be simultaneously factored when we do Cholesky factorization. And then we have couplings, and we have a relatively small block here. Okay, this is not the original finite element model. There would be many more couplings there. On the other hand, of course, we have multiple values. So after solving, we enforce the continuity constraints by averaging across the interface. And in FETDP, instead, we try to enforce the continuity by using Lagrange multipliers. So the partially subassembled stiffness matrix of this alternative finite element model is used to define the preconditioner. The primal variables are global component of these preconditioners. And also, this approach, if you have the right number of primal variables, all the matrices encountered will be positive definite in the vertex. So much of the work using Cholesky's algorithms for finite element problems using individual processor on a parallel machine. Okay, so the whole structure of the algorithm is quite simple and it has a modular structure. And if we find better local solvers, we can just plug them in. The local problems, as I said, are independent of each other, so they don't require inter-processor communication. So continuity is restored by computing the weighted average across the interface. And this leads to since we change the value, then we get non-zero residuals at the nodes next to this. And So in each iteration, we use subdomain Dirichlet to eliminate those. For the BDDC Deluxe, this is not required actually. This will automatically happen anyway. So for a scalar elliptic problem, the model I showed is adequate. The primal spaces are good, and we can get condition number bounds of this type. This is a logarithm of the number of elements across a subdomain. And then the results can be made independent of the jumps. And the condition number, as I said, determine the rate of convergence of the entire algorithm. So we have good numerical results. But if you try to do exactly the same for a 3D problem, you have a relatively slow convergence. So what you have to do then is to introduce new sets of primal variables. And the choice of primal variables is the main issue for any application that you're facing. There are different rules, different recipes, good recipes for different types of elliptic problems. So for example, for 3D elasticity or 3D scalar elliptic problems, we should use averages over individual edges and sometimes first moments. That will give a small but very powerful primal space. And if you change the variables, then you can still work with the same matrix structure that I showed. This arrow shape. Okay, now, so reliable recipes exist for selecting small sets of primal variables. Yes, okay. And also, these algorithms have been implemented in PETC-based codes. PETC is really a very important development for parallel computing. It's ran out of Oregon National Lab, but it's actually a loose collection of about a dozen people at any time located at different places. They represent, I think, in many ways, the state of the art of this type of parallel computing. And one of the main contributors to this recently is Stefano Zampini, with whom I also have the privilege of working often. And he also has introduced more than 2 levels of BDDC. You take the problem for the primal variables, and then you apply essentially BDDC once more, recursively, or many times actually. But typically you do it no more than 3 times these days. Okay, so what do we have here? Well, we have a completely local space where we allow discontinuities at all interface points. We have the partial assembled space where the primal variables are continuous, but the others are not, and we have the fully assembled thing. So no constraints, continuity at every point, and common values to the primal variables. These are the obvious spaces. Okay, so if you change the variables, as I said, we can introduce, we can separate these things out clearly, which simplifies the presentation and also makes the method better. So after eliminating the interior variables, we end up with what's called Schur complements. And they represent actually the energy of the harmonic extension, the minimum energy extensions, or boundary of interface data to the interior of the subdomain. And we see here, we split the space into dual and primal. And then we can partially subassemble these SIs and obtain the matrix S tilde, which is important. Okay, so we work in this partially assembled space, and we will restore continuity by applying a weighted average operator ED, which maps partially assembled space into the fully continuous one. So here's a description of BDDC. First you compute the residual for the fully assembled Schur complement, which you can do subdomain by subdomain and then merge these. And then you apply the transpose of the average operator, and that makes you, for a right-hand side, for the partially sub-assembled linear system. And you solve that, and then you apply the average. And then you have completed one iteration. So this last, as I said, you might get non-zero residuals at nodes next, which you can eliminate. Okay. All right. I made that point already. Okay. So in any applications, it turns out, and that's very convenient, the S tilde norm of this average operator determines, it's an upper bound for the condition number of the method. So when you do theory, you focus on this. Okay. So we should choose an effective set of primal constraints for each subproblem, for each problem, and we also a recipe for the averaging. And the traditional averaging for BDDC was found not to work very well, always for 3D problems in H-curve. And Dorman gave a talk in the 20s domain decomposition conference on that. And then eventually, some years later, it resulted in a joint paper with Dorman in the Communication of Pure and Applied Mathematics in the Current Journal. So alternatives were found, which were the Deluxe methods, and they were also very robust for 3D problems. And this has resulted in a paper which has appeared electronically and comes out in print form later this year. And this involves, in addition to myself and Dorman and Zampini, a former student of mine, Duxenov. And what happened was that when we looked at H-curl and H2 problems, we have two material sets of parameters. And we found a way of dealing with that by doing the Deluxe scaling. So there are also now 3 papers on isogeometric elements together with 4 Italian people, excellent people, and they have appeared. And this paper about elasticity is about to appear. And also there is very strong results by Andres Leminden, by a former student of mine, another Korean student. And also it turns out that BDDC Deluxe is also very important in adaptive choices of primal spaces. And I have a joint paper with Juan Calvo on that, which appeared in 2016 in ETNA. Okay, so what is Deluxe? So let's look across the face. We also have edges, right, which are common to more than subdomains. But I'm going to give you the formulas for a face, which is a little simpler. First of all, we can compute a Schur complement. This is actually the sub-matrix of the Schur complement for the subdomain omega k, restricted to the face. And here's the formula. This is exactly what you get when you eliminate the interior variables. And the Deluxe averaging looks like this for a face. We take the values, these values typically are not the same. they should be the same, of course, in convergence, multiplied by these two complements, and then we solve this system. We see here, if these happen to be the same, this is just the identity map. So the action of this can be implemented by solving the Dirichlet problem on the union of the two subdomains and the interface in between. And this can be significantly costly. However, it turns out that instead of using this rather large problem, it often works very well when you just take the points on the interface and those in the two layers next to, one or two layers next to it. And then there's no luxury involved anymore. It's cheap. Okay, so similar formulas are developed for edges and other equivalence classes. And then we have more than two, typically, Schur complements involved. And ED assembled, it's a local process. Once we have formulas for each individual equivalence class, and then we assemble what we get. So the core of the estimate, as I already mentioned, is this formula that condition number of the preconditioned system is bounded by the S tilde norm of the average operator. This is very good because it focuses the mind. We know exactly what we have to look for. So, now, one thing about the BDDC Deluxe is that we can reduce the bounds to individual subdomains, which is very important, actually. The arbitrary jumps in two coefficients can often be accommodated, as for H-core and H-dip problems. The traditional BDDC analysis requires an extension theorem, which can be difficult, especially if you have bad interfaces, but the Deluxe version does not. Okay, so now what we have to do, we have to estimate instead of working on this is what we would like to estimate, this is the average, and this is the energy of the phase function, the average phase function, okay? Yes, I know that, but we can instead work with this quantity. Once we have a bound for this, it's very easy to get a bound for that. So RF is the restriction of a function on the interface to the face. And simple algebra shows that we have this formula here. And now we get a rather long formula here. Right here we have the energy associated with this minus the average, and we have no less than 5 operators here. But if we look at the contribution to the same phase from the other subdomain, and then add these contributions up, we get a much nicer looking formula. It's just the average. This is a jump across the interface. And here we have this interesting expression. It's called a parallel sum. And the parallel sum of two positive definite operators are simply defined. We write it with a colon. It's defined by this, just like here, okay? And we note that this parallel sum is obviously bounded by A and by B. And also there is an interesting formula worth knowing about, that if you look at this, you can compute it by taking the infimum of any splitting of C into X plus Y of this. And then it follows that you can actually bound this quantity by two quantities, where this is the common primal, arbitrary primal element that you stick in here. And here we have, this depends on one subdomain and this on the other. So we have this localization. And now we can estimate, so I call this is just the dual part, which I call this. Okay, so if you can estimate this by this quantity, what is this? Well, this is you take the same function and you extend it to the rest of the subdomain boundary using minimum norm extension. If you do that, then you can estimate the energy of any function which has the restriction of which to the phase is equal to this by the energy associated with the subdomain SI. So it turns out that this is a Schur complement of a Schur complement. And here's the formula for this. And where F prime now is the complementary set of the interface omega I. Sorry, this should be F, not R. Okay, so routine bounds can now be applied, so-called phase lemmas. And we end up with a condition number bound, which looks like this. Constant times log squared. Now, using the ideas of Dorman, we can now turn this into adaptive method. We look at these two parallel sums, and we compute we look for the eigenvectors associated with the largest eigenvalues, and we put them in the primal space. And then we can get improved bounds, and also we can in advance know how well the iteration will work. We can set a tolerance, and we can enforce that tolerance by increasing the primal space appropriately. So this device allows us to handle problems experimentally with huge changes in the subdomains inside the subdomains. And the primal spaces actually do not grow to a great deal. It turns out that the eigenvalues often decay very rapidly. So just peeling off a few will give us greatly improved bounds. Okay, and now we also have to do this for edges, and that's less well understood when it comes to the adaptive methods, but still there has been considerable success. So the best work on this is a paper by Dorman and Pechstein, which appeared last year, I think, in Electronic Transactions and Numerical Analysis. For H-Div and H-curl, considerable efforts have been required to get bounds dealing with these Schur complements, essentially. Okay. Oops, what happened? Okay, so just what are the H-curl problems we have looked at? Well, we have two sets of variables here. Here we have the curl operator, and here we have an L2 term. And these are non-negative. And for piecewise constant coefficients, we assemble the energies with different alpha i's and beta i's. Okay. Now, for H-curl, we typically use Nedlec elements, and and it was really quite tricky to find the appropriate primal space here. Now, we could actually draw upon earlier work from around 2005 by Andrea Toselli. And you have to change variables associated with the wire basket, which is the union of the edges. And you have to have 2 degrees of freedom per subdomain edge minimum for the primal space. Then you have success. And then we can get stable decompositions and good bounds. This was not easy. It took 3 years to complete this work, in spite of Toselli's previous effects. Okay. Okay, so I think I should skip this because time is short and I want to do a few other things. But anyway, we improved bounds. We got essentially logarithmic bounds. The mass-dominated case is not fully handled, but okay. So here is an example of BDDC Deluxe in action. So we have constant alpha, beta is the same everywhere. Constant alpha, this is the number of subdomains across. So for example, here we have 12 to the power 3 subdomains. These are relatively small problems. And you see we reduce the residual norm by 10 to the minus 8, or 10 to the 8. And we see the iteration count actually stays the same essentially. Let me see here. When we change from mass-dominated to curl-dominated, things are not all that different. And we see condition numbers are very nice, between 2 and 3 often. Now, again, small problems here. What happens when we change the number of elements across the subdomain? Nothing much. We expect a logarithmic growth, right? And we see here that things are in pretty good shape. Again, we bring down the residual norm by a factor 100 million. Okay, now we have checkerboard arrangements and material properties, and we have tested earlier scalings. And here we have the deluxe scaling and the E-deluxe, the one with very thin subdomains. And we see the iteration counts are very satisfactory here, but here things are not working very well. Now here is a larger problem. We have 1,000 subdomains, and they are not boxes. They are created by a mesh partitioner. And we have here random values of beta and constant alpha. We see full deluxe, 1 layer, and 2 layer deluxe. 2 layer deluxe is almost as effective as this, and it's a bit cheaper. So HDiv, I already cited the work by O, Dorman, myself, and Sampini. Here is the original problem, positive definite symmetric problem. And we got bounds which are completely independent of the choice of alpha I and beta j. And crucial to this work and the HGOL work are results by Hiptmeyer and Shu, which have also been very important in the development of multi-grid methods for this type of families. And the bounds we have in HDiv are very clean cut. It looks like this. And they're often very small. For smaller problems, we found condition numbers in the range of 2 to 5, which is very satisfactory. And we found examples where the original averaging resulted in much worse conditioning. And we also found good results with variable coefficients inside subdomains. Okay, and for the rise in the middle plates, it's an interesting case. I mean, we love problems which are extremely ill-conditioned, and then coming up with preconditioners which have very tiny condition numbers. So for example, if you have a very thin rise in the middle plate, we might have a condition number of problem which is 10 to the 11, And then when we apply the BDDC Deluxe, the condition numbers rarely are more than 4. And here are some problems, which shows that we are doing some large problems. A billion variables, each div, with 30,000 degrees of freedom. And you see here this on a big machine at Kaust in Saudi Arabia. The solver phase takes about a second for using 32,000 subdomains. And the factoring is also very satisfactory. It's the lowest curves here that are relevant. And also we can do problems which have terrible variation in the coefficients inside the subdomains. We can't do theory for that, except that we use adaption and we use 3 levels. Without adaption, the results are pretty awful. But with adaption and the 3rd level, we can get a solution in about 5 seconds for problems which have 2 billion variables. Okay, just a few words here about the isogeometric analysis work. So the co-workers are Lorenz Barada Vega, Luca Pavarino, Simone Scacchi, and Stefanos Sampini. And they had worked, these guys, they had worked earlier with BDDC, with classical interface averaging. And then I visited Pavia and got them to try the BDDC Deluxe, and it improved the iteration counts, and everything became much more robust. So what is isogeometric analysis? Well, the main idea is you use, instead of finite element functions, you use what's called non-uniform rational B-splines. And where do they come from? They come from computer-aided design. So if you start out by doing computer-aided design, which is typically the first step in computational engineering, then the advantage of this is that you can then use the same spaces and a Galerking method simply to set this up. The resulting stiffness matrices are extremely ill-conditioned, especially when you increase the degree of these B-splines. So that, of course, is very attractive to somebody like us. And one difference between finite element is that you have fat interfaces. There are more than one line of nodes. It's not the nodal. These NURB functions are not nodal. So you have fat interfaces. So potentially you have a very large portion of your unknowns on these fat interfaces instead of in the interior. So then the question arises, can we use adaptive methods to select relatively few primal variables, much, much smaller than all these degrees of freedom that we have on the fat interfaces? And the answer is that we have been successful. And they also have obtained bounds for the condition numbers, typical log squared bounds for lower order cases. And we have observed in our experiments that iteration counts do not grow with the degree of the underlying B-splines. We don't know why. And our work includes adaptive choices of primal spaces. And recently we went from scalar elliptic problems to 3D elasticity. Okay.